So first, in order to rank the molecular forces and find out the boiling points of different molecules, first I want to revisit the difference between ionic and covalent bonds, just as a little refresher. So ionic bonds are molecules that occur between a metal and a nonmetal. So between a metal and a nonmetal. So anytime you see a molecule that's between a metal and a nonmetal, you can automatically assume it's ionic. So what are metals and nonmetals? On the periodic table, you see this staircase over here by the boron and aluminum. There's a little staircase that is usually marked in bold on periodic tables, and this little staircase is what divides the periodic table from the left side, which are all metals, and the right side, which are all nonmetals. So everything over here is a nonmetal, and everything over here is metal. Now, the exception to this is hydrogen. Hydrogen is not considered a metal. Hydrogen, when we're talking about this, hydrogen actually belongs over here in the nonmetals when we're talking about ionic bonding. So that's the exception to the rule. But besides hydrogen, everything on the left side of this staircase is a metal, and everything on the right side is a nonmetal. So anytime you see a molecule that is a bond between a metal and nonmetal, that's going to be ionic. So if we have magnesium over here and oxygen, magnesium oxide, that would be an ionic bond. If we have sodium chloride, that would be an ionic bond. So an ionic bond is between a metal and a nonmetal. Now a covalent bond is going to be between nonmetals. So between nonmetals only. So once again, if we look at the periodic table, the nonmetals is over here on the right side, plus hydrogen. Hydrogen also counts as a nonmetal. So a covalent bond is going to be between two or more elements that are only from the right side of the periodic table, like oxygen and fluorine together. Those would be both nonmetals, so that would be a covalent bond. Carbon, carbon monoxide, carbon dioxide, those are nonmetals. Carbon and oxygen, those are nonmetals, so that's going to be a covalent bond. Now, ionic bonds, the bond that happens between ions, between the metal and nonmetal ions, happen because of the ionic charge of each element. So bonds because of the ionic charges. So ionic bonds aren't going to be like just sodium and chlorine. It's going to be the ion of sodium and the ion of chlorine. So if we have sodium chloride, this does not mean that the sodium in its natural state bonded to a chlorine atom in its natural state. It has to be the sodium ion, which is a +1 charge, and the chlorine ion, which is a -1 charge. And then they come together, and the positive and negative cancel each other out, and it turns into sodium chloride, which has a neutral charge. It doesn't have any charge at all. Now the covalent bonds, they bond because of the octet rule. So bonds because of the octet rule, because the elements, not the ions, but the regular elements, not in their ionic state, they want to have 8 electrons in their outer shell, in their outer valence shell. So they're going to bond to another element whose electrons can fill those slots. So they can they can share the electrons and both have 8 in their outer shell. So for instance, methane is CH4, and carbon has 4 bonds around it, has 4 electrons around it normally, but it wants 8 electrons around it in its outer shell. So it will easily bond to hydrogen, which has 1 electron in its outer shell, well, 1 electron period. So they help each other out, and the hydrogens allow the carbon to be surrounded by 8 total electrons instead of just the 4 that the carbon comes with. So this is going to be an example of covalent bonding. That's ionic bonds and covalent bonds, 2 totally different bonds. Just remember, if you can't remember all of this, just remember ionic bonds are between a metal and a non-metal. So if you see a metal and a non-metal together in a molecule, that's automatically an ionic bond. You can just safely assume that. If you see 2 nonmetals together, you can safely assume that that's going to be a covalent bond. Okay, so now that we are straight on what an ionic bond is versus a covalent bond, now we can start talking about boiling points. Ionic bonds are going to have the highest boiling point. The attraction between the positive and negative ionic charges are so strong that it takes a whole lot of energy, meaning a higher temperature, to break those bonds apart and to separate the ions from each other, and therefore to turn a liquid into a gas, to boil the liquid until it's a vapor. So ionic bonds have the highest boiling point. So if you have to choose between a molecule made of ionic bonds and a molecule made of covalent bonds, the ionic bonds win. Now, out of the covalent bonds, there are 3 different types of molecular forces within the covalent bonds. The top one, the one out of the covalent bonds, the one with the highest boiling point, is going to be the hydrogen bond. So, you might see it like this, an H bond, but it's for hydrogen, H for hydrogen. And a hydrogen bond is anytime a hydrogen is bonded to a fluorine, an oxygen, or a nitrogen, and that's it. I always think of hydrogen, phone, home. So phone, home. So fluorine, oxygen, nitrogen bonded to a hydrogen. Phone, home. Anytime the hydrogen is directly bonded to a fluorine, an oxygen, or a nitrogen, that is a hydrogen bond. And that is going to have the highest boiling point out of all the covalent bonds. Next, we have the dipole forces. And I explained in a previous video what the dipole forces mean, what the dipole is. And so all polar molecules, if the molecule is polar, all polar molecules have dipole forces, because by definition that's what a dipole is. It's when, like, let's say you have water and the oxygen is more electronegative than the hydrogen, so the oxygen is going to pull all the electrons toward it, so therefore it's going to have a partial negative charge by the oxygen, and since all the electrons have moved away from the hydrogens, the hydrogen end of the molecule is going to be positive. So this molecule has one positive end and one negative end, so that makes it polar. And if it's polar, it's going to have dipole forces. And so dipole forces are going to have the next highest boiling point um, after the hydrogen bond in the covalent bonds. And of course, everything has a lower boiling point than ionic bonds, because remember, ionic bonds win. Then after the dipole forces, you have London dispersion forces. Now, all covalent bonds have London dispersion forces. So this is the predominant forces in nonpolar molecules, but they also happen during polar molecules as well. But when you get a nonpolar molecule, the only kind of force that is going to bond the elements together, these molecules together, if they're nonpolar, the only force that can bond them together are the London dispersion forces. And if the molecule does not have ionic bonds, it does not have hydrogen bonds, it's nonpolar, so it doesn't have dipole bonds, then the London dispersion forces are going to be what bonds the molecules together. So in order to rank molecules for what has the highest boiling point, you want to ask yourself two questions. First, you want to ask yourself, is this molecule assembled by ionic or covalent bonds? If they're ionic, you can stop right there. It has the highest boiling point. Ionic molecules are going to have higher boiling points than covalent molecules, period. And then after that, if it's covalent, if it's not an ionic bond, if it's a covalent bond, what kind of bonds are present? Is it a hydrogen bond? Is it dipole-dipole bonds, or is it just the London dispersion forces? So let's say we have three different molecules that are created by ionic bonds, and you need to rate these in order of their boiling points. And we have up here in the upper left-hand corner, I have the different types of molecular forces, and of course ionic is the strongest. And then after ionic, you have the covalent bonds, the hydrogen bond, dipole, and London dispersion forces. But let's say we're not dealing with any covalent bonds. Let's say we're dealing with all ionic bonds. How do you compare ionic bonds to each other to find out which one has the highest boiling point? So see, we have here three different ionic bonded molecules. We have sodium chloride, we have magnesium oxide, and aluminum nitride. So what we're going to do, these molecules are each connected by their ions. So NaCl is the ion Na plus, and Cl is the ion Cl minus. And when they come together, the plus and the minus cancel each other out, and so you end up with NaCl, which has a neutral charge. It has no charge. But so what you do is you separate these out into their individual ions, and as you can see, sodium has a +1 charge, and chlorine has a -1 charge. So for getting the plus and the minus, we're just going to take the number of charge it has, in this case 1, and we're going to multiply them together. So 1 times 1 equals 1. Now, magnesium oxide, if you separate the magnesium from the oxygen, you're going to get magnesium, and magnesium has a 2 plus charge, and oxygen has a 2 minus charge. And so we're going to take that 2 from the magnesium's charge and that 2 from the oxygen's charge, multiply them together, and you're going to get 4. And then aluminum nitride, you're going to have aluminum, which is a 3 positive charge, and nitrogen, which has a 3 negative charge. You're going to take the 3 from the aluminum and the 3 from the nitrogen, and you're going to multiply those together, and you're going to get 9. So whichever one of these has the highest number is going to have the highest boiling point. They're going to have stronger molecular forces keeping them tightly bound together. So it's going to take more energy, more heat to cause it to boil. So it's going to have the highest boiling point. And so this number 1 over here, the sodium chloride, is going to have the lowest boiling point in comparison to these 3 ionic bonds. These 3 molecules made from an ionic bond. This is going to have the lowest boiling point because the charges multiplied together is only 1, so it's going to be weaker. So it's going to take a lot less heat in order to cause it to boil. And so that's how you compare the ionic bonds, different molecules created from ionic bonds, and their boiling points. And you can be able to rank which ionic molecule has the highest and lowest boiling point. So what if you want to rank different hydrogen bonds molecules and find out which has the higher boiling point if they both have hydrogen bonds? So again, up here on the upper left corner of your screen, I have the different molecular forces and their ranking according to highest boiling point to lowest boiling point. The ionic is the highest boiling point. And then we have covalent bonds. And under those covalent bonds, we have the hydrogen bond, the dipole-dipole bond, and the London dispersion forces. So right now we're working on the H bonds. What if we are comparing 2 different molecules and they both have hydrogen bonds in them? And so how would we know which one has the higher boiling point? So for an example here, we have CH3, CH2, 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 OH. So this OH is a dead giveaway that this is going to be a hydrogen bond. Because remember, a hydrogen bond is a hydrogen bonded directly to a fluorine, a hydrogen bonded directly to an oxygen, or a hydrogen bonded directly to a nitrogen. And that's it. That's the entirety of hydrogen bonds. It has to be connected to one of these 3 elements, the fluorine, the oxygen, or the nitrogen. Remember, phone home. Phone home. So we have this OH group, it's called a hydroxyl group, which is a hydrogen bond in this molecule on the left. And then we have this molecule on the right that looks kind of similar, CH3, CH2, OH. And so this, of course, also has a hydroxyl group, an OH to it. So that means this also has a hydrogen bond. So these look kind of similar. How can you tell which one has the highest boiling point? Well, the answer is pretty simple. Since this carbon chain on the left is a lot larger than the carbon chain on the right, it has more atoms in it. This is going to also indicate that it has more London dispersion forces. So that means it's going to have the higher boiling point. Because it has the hydrogen bond, but then it has these supporting London dispersion forces, and it'll in a lot more higher quantity. So that means it's going to be held together more tightly, and it's going to require a lot more energy and therefore a higher temperature in order to boil and for the molecule to break apart into a gas. This one over here on the right only has uh, 2 carbon chains instead of the 4 on the left, so that's going to be a lower boiling point. So that is how you compare boiling points uh, between molecules that both have hydrogen bonds. Now, of course, if we're comparing these hydrogen bonds molecules to a molecule made from an ionic bond, the ionic bond will win because ionic bonds um, are the strongest bonds, and so their ionic bonds are going to have a much higher boiling point than any covalent bonds. But out of the covalent bonds, if we don't have any ionic bonds, then hydrogen bond is going to be the winner out of the covalent bonds as far as highest boiling point. But if you're comparing 2 different molecules and they both have hydrogen bonds, then you need to look at the size of each molecule, because that's going to tell you who has the most London dispersion forces, and that tips the scales. The most London dispersion forces will tip the scales and make that molecule have the highest boiling point. Okay, so continuing on with that, now we have several molecules that have all different types of bonds, all different types of molecular forces, and let's rank these in order of highest to lowest boiling point. So we have water, H2O, and then we have hydrogen sulfide, and then we have hydrogen selenide, and I don't know if that's the right pronunciation of that, and then we have magnesium oxide. And up here in the corner, as usual, I have the ranking system from highest boiling point, which would be the ionic bonds, to lowest boiling point. So first, let's look at these 4 molecules and try to figure out what kind of molecular forces are binding these together or bonding these together. So first we have over here H2O. Now if you notice something, you should notice right off the bat, H2O is going to have hydrogen bonded to an oxygen. Now what is it called when hydrogen is bonded to an oxygen? That is called a hydrogen bond. If the hydrogen is bonded to a fluorine, an oxygen, or a nitrogen, that's a hydrogen bond. So a hydrogen bond is a form of a dipole bond, but it is the highest boiling point. It's the tightest bond. And so we know that this is going to be have dipole forces as well, because all hydrogen bonds are dipole bonds. If it has dipole bonds, that means that this is going to be polar. And all covalent bonds are going to have London dispersion forces. So see, all covalent bonds have London dispersion forces in them. Now the next one, H2S, this is not a hydrogen bond because hydrogen bonds are only hydrogen connected to fluorine, oxygen, or nitrogen. Now this is connected to sulfur, so this is not a hydrogen bond. But it is polar because when you draw it out, you have sulfur, and then it's a bent molecule, and hydrogens are on one end of it. The sulfur is more electronegative, so the sulfur is going to have a partial negative charge on the sulfur end of the molecule, and the hydrogens end of the molecule is going to have a partial positive charge. So that's going to create a dipole moment, a dipole. And so this is going to be polar. So if it's a polar molecule, all polar molecules are dipoles. So we know this is going to have dipole forces in it. And since it's a covalent bond, it's also going to have London dispersion forces. Now, H2SE, hydrogen selenium, is going to have similar properties. It's also going to be bent and have two hydrogens, one coming out of each side, and the molecular structure is going to be bent like this. And selenium is going to be more electronegative than hydrogen, so selenium is going to suck up all the electrons, so it's going to have a partial negative charge there. And the hydrogen ends are going to have a partial positive charge on the hydrogen ends, and so that's going to create a dipole where all the electrons are moving toward the selenium. So that means it is polar as well. And if it's polar, then it has to have dipole forces, because that's what dipole forces are. It's the polarity of the molecule. And all covalent bonds are going to have London dispersion forces. Now let's look at magnesium oxide. Now magnesium oxide, if you look at the periodic table, magnesium oxide is a bond between a metal, here's magnesium, and oxygen, a nonmetal. So what do we know about this automatically, because it's a metal bonded to a nonmetal? That's right, that means it's automatically ionic. So we can stop right here and know that magnesium oxide is an ionic bond. So we know that magnesium oxide is going to be ionic. So we can stop right here and know that magnesium oxide wins. Magnesium oxide is going to have the highest boiling point because highest BP. Because up here in the upper left corner of the screen, remember the ionic bonds have a higher boiling point than any covalent bonds, no matter what the covalent bond is. So, winner. Okay, so now that we've got the highest boiling point, magnesium oxide, now we're dealing with the rest of these, the other three of these, which are all covalent molecules. So if you look up on your chart, covalent molecules include the hydrogen bond, the dipole forces, and the London dispersion forces. Now we have a hydrogen bond with water here, H2O. It's got the hydrogen bond. And so we know that H2O, out of the covalent bonds, H2O is going to be the winner for the highest boiling point out of the covalent bonds. Now magnesium oxide is still the overall winner of all of these, but just comparing these covalent bonds, these three, after magnesium oxide, H2O is going to have the highest boiling point because it has the hydrogen bond. Now, what about these leftover two? We have H2S and H2SE. Now, they're both polar, so that means they both have dipole moments in them. and they're covalent bonds, so they both have London dispersion forces. So how can we tell which one's going to have the higher boiling point than the other one? Well, since they both have dipoles in them, which means they're both polar, what we're going to do is we're going to look and see which one is going to have the most London dispersion forces in there. And the way we do that is we count the number of electrons that is in this that are in these molecules. So we have hydrogen. Hydrogen each has one electron, and there's two hydrogens here. So that makes 2 electrons for the hydrogen in this and 2 electrons for the hydrogen in this. So really it all boils down to the sulfur or the selenium, which one is larger. And for that we can look at the periodic table. And so in the periodic table, here is sulfur, and its atomic number is 16, so that means it has 16 electrons. And here's selenium below it, and selenium's atomic number is 34, so that means it has 34 electrons. So selenium wins in this. It has more electrons. So back to our page here, we have selenium with 34 electrons. And so this hydrogen selenium is going to have a higher boiling point than the hydrogen sulfide, the H2S. So in order of boiling points from largest to smallest, we have the magnesium oxide, because that's an ionic bond, and then we have the H2O, because that's a hydrogen bond, and then we have hydrogen selenium and hydrogen sulfide. And that is in order of boiling points. So the highest boiling point would be the magnesium oxide, and the lowest boiling point would be the hydrogen sulfide.